But what I want to go through now is some stuff that hopefully will be of use to us as you continue to work through the homework. Because I think what we're doing now, most of it, the math is not particularly hard, but what's hard is figuring out what you're supposed to do and how to deal with sign conventions and which things are, which things stay around and which things are zero and how to deal with all of that. So we're going to look at another example for of Reynolds Transport Theorem with F equals ma, the momentum, and we'll spend pretty much the rest of class going through, well, we'll go through this example pretty slowly, and then I'll just have a couple of points hopefully at the end specifically. So we'll jump into another example. Reynolds Transport Theorem example. So let's say, and I'll draw this kind of big because last class I didn't draw it big enough. Okay, let's say we have a section of pipe like this. So this is our section of pipe. And at one side of the pipe, there's a cap, which has a hole in it. So there's an end cap stuck on that pipe with a hole in it. There's going to be water flowing through this pipe with a flow rate Q. Q equals 0.57 meters cubed per second. So we know what that flow rate is. Our water is going to be flowing through this pipe and it's going to be shooting out of that little hole in a jet. So there's going to be a jet that's coming out of here like that. So we have water shooting out of there. A couple of key dimensions that we know. We know the diameter of this pipe is 10 centimeters or 100 millimeters. We'll just work in millimeters. 100 millimeters. And we know the diameter of the jet here is 38 millimeters. And then the last things that we know about the pressure. So we know that the pressure here, P equals 138 megapascal gauge, which is a high pressure, very high pressure. And we know that this is shooting out from this pipe, it's shooting out into the atmosphere. So the pressure over here, P equals P atmosphere. So what we want to figure out is the force that it takes to hold our end cap on. Right, to keep that from flying off the end of our pipe. So the first thing we need to do is put axes on our problem. So in this case, we'll define the x direction as down the pipe. Then we can jump to, okay, so this is a question, and some of these questions, the whole idea of Reynolds Transport Theorem is a way to use physical laws and apply them into systems like this, where you have stuff going in and stuff going out. So whether you're using like conservation of mass, F equals ma, conservation of energy, the the second law of thermodynamics, like whatever it is, whatever physical law you're talking about. Reynolds Transport Theorem just gives us a way to look at a system like this and apply that law in this context. Right, this kind of a system, it has to obey all of those different physical laws because they're not like context dependent. Reynolds Transport Theorem just gives us a way to apply it in this context. So we care about, in this problem, forces. So we care about F equals ma, right? That's the thing that is going to be the most important for this. So we'll start with the linear momentum equation. So the linear momentum equation, the general form is this. Okay, is this with this kind of weird notation. So Fx is the net force in the x direction acting on our control volume. That first integral term is, we're talking about momentum, so that's how much momentum is inside of the control volume. How is that changing with time? And then the second term is how is momentum coming in and how is it leaving? Right, this is, momentum is what? Mass times velocity. So this is, right, that's velocity times mass, right? Density times velocity is mass, or sorry, density times volume is mass. This is velocity, and then this whole second term is mass flow rate. Density, velocity, area. So that we have a mass times velocity there too, because we're talking about momentum. So that's kind of how these pieces fit together. The notation looks a little bit weird, but that's why it looks the way that it does. The way that we're gonna typically use that is not when it looks exactly like this. Because the notation is weird, we start to get into integrals, and we very quickly like lose touch with what's physically happening. And like, how do we think about what's physically happening? And I want to get you guys to build like some intuition about how forces work and how we can think about some of these things without getting lost in the land of calculus and integrals. So there are a couple, two of the problems on the homework this week. You're going to go through and do the detailed integration to figure out like how do these kinds of weird looking integrals work, because I think there's some value in that. But most of the time, we're going to live outside of the land of integration just to try to be able to develop, like keep the math a little bit simpler so we can focus on the concepts more than the details of like doing the calculus. So basically all of the time in this class, we're going to have two different things that help us. Steady state. So steady state means that the time derivative, ddt of anything, is equal to 0. So if something is steady state, if it's not changing with time, you take a time derivative and that thing dies. So any time derivative, right, this whole first term, the ddt of the momentum inside the control volume, that whole term will die away because the time derivative kills it because it's steady state. The second simplification that we're going to make, again, not all of the time, but nearly all of the time, is uniform velocity. So if we make this assumption, and this one is steady state, like we have a lot of systems in the real world that are steady state. This system here, you could think of like, you're just holding it and it's shooting out at the same velocity. That's a steady state process. The uniform velocity is not true, but it's handy because it turns integrals into sums. Which is, right, multiplication and summation are easier than integration, although they're the same thing, right? Doing an integral is just doing a sum a lot of times over a whole thing that everything happens to be changing. So they're the same thing. But uniform velocity gets us out of the land of calculus and into just straight multiplication and sums. So with these two things, again, we're not going to use it all of the time, but most of the time. This gets us to a sum now over all of the control surfaces that we have of u rho v dot, not dA, just A. Right, so these directly simplify our linear momentum equation down into this. It's still going to be a little bit weird and unwieldy, and we'll take some practice to get used to how to use this, but it's just functionally, it's going to be easier to do than, and it's the same thing, easier to do than to deal with the integration. So this, especially the second thing, this is not strictly true. But it's useful, and it's useful for us to get an idea of what the answers are, but also just to get like an idea of how the physics of this stuff actually works. So that's mostly what we're going to deal with. Although, like I said, we will have a little practice to do some of the actual integration and see how like the integral piece by themselves, not in one of these broader problems, but how just the integral works kind of by itself. We'll get some chance to do that. The first step that we need is kind of once we identify, we're talking about momentum, we're talking about the x direction, we have these simplifying assumptions, this is the equation that we're starting with. We need to first identify a control volume. So our CV will be where, right, this is like, what do you choose as a control volume? You choose the place where the interesting stuff is happening. So what is interesting with regard to F equals ma? Where are accelerations happening? So where do you have changes in velocity? If there's no change in velocity, F equals ma is a really boring equation because it's 0 equals 0. So you have to have something, where are accelerations happening? Okay, acceleration obviously meaning change in speed or direction. Okay, so where is that specifically? And this was like in the thing that, like the in-class thing that you guys did for today, this was kind of the weird part to figure out too. Like, what is the control volume in that? Like, what section of the corn are we looking at? So a lot of times choosing your control volume is not super straightforward, but it's where things are accelerating, where they're changing speed. So we can think of it for this, well, really far to the left, it's just going to be flowing down the pipe, just hanging out, not doing anything special. So no accelerations really far to the left. After it shoots out of the hole, then it's going to just, go on its merry way, but not really. Eventually, right? It'll experience forces due to gravity, and it'll be different things like that. But that's not really the part that we care about. We care about when it's like kind of in this weird transition point, when it's speeding up kind of to go out of that hole. So we care about, I don't know, something maybe like this. And then, a little ways out of the hole, possibly. So that would be our control volume, right? And the control volume is the fluid itself. Because that's kind of right, we're looking at these things as like what is happening with the fluid. So the fluid itself, there are two control surfaces. Control surfaces are where things are going in or out. So two control surfaces, this would be surface 1 on the left. This would be surface 2 on the right. Right, where you actually have like stuff entering and leaving that control volume. So the control volume is the fluid itself. It's that funny shaped box where all of our accelerations are occurring inside of that box. Okay, so now we have to look at our equation here, and we're doing this sum across all of the control surfaces. So what that will look like is fx u1 rho v1 dot a1, right? We only have 2 plus u2 rho v2 dot a2. And you would keep adding, if you have more control surfaces, you keep adding it across whatever control surfaces you happen to have, wherever something is going in or out. Right, when we did this like funky shaped joint with like, inlets and a little leak coming out the side, then there were 4 control surfaces. There were 4 areas, 4 points where stuff could be going in or out. So those are the points where things are going in or out. Now evaluating this, we have to look at, okay, the next step is to do this dot product. So U1 rho, the dot product you're looking at, so this is how we handle sign convention, is by doing it in vectors and doing it with dot products. So this is going to handle the sign convention for us. Our sign convention is going to be, the nice thing about doing it like this, right? I can move things. So our sign convention is going to be such that, right, our areas here, that's A1, that's A2. The area is always going to be the outward facing normal. So it's always going to be pointing out. It's just a convention. We could have them always pointing in, but we do it this way because then we do it the same way every time, and right, it gets us the right answers. So it's just a way to get the, like, what's going in, what's going out, and get those all straight. So that's our sign convention. So our fluid is going from left to right. So the velocity vector is pointing to the right. A1 is pointing to the left. So that dot product is going to be negative. So this is negative U1 A1 plus U2 rho. Now this one, again, because it's the outward facing normal, our velocity is still pointing to the right. Our area vector is also pointing to the right. They're pointing in the same direction, so that's a positive. So this is now U2 A2. Okay, so our next step is to figure out how to use conservation of, how to figure out what the velocities are. So we're just kind of dealing just with this right side first, and then we'll deal with what's happening on the left side of the equation after this. So let's look at now conservation conservation of mass, or what sometimes we'll call continuity. So continuity, again, this would be conservation of mass in the framework of Reynolds Transport Theorem. Would be under the same assumptions that we're dealing with right now. It would be 0 equals V dot A, which would be rho U1 A1, it would be negative plus rho U2 A2. Or we could write it this way, right? Rho U1 A1 equals rho U2 A2. In equals out. Right, so the rho U1 A1, before we did any of this confusing stuff, you guys figured this out on your own. That's the mass flow rate into the system at side 1. The other one is the mass flow rate out of the system at side 2. Those have to be equal because conservation of mass. We know the flow rate. So we're given Q equals 0.57 meters cubed per second equals equals U1 A1 equals U2 A2. So we're given the mass flow, or we're given the volumetric flow rate Q. Q is going to be the variable that we use typically for volumetric flow rate. We'll use that throughout the class. I think this is the first time you guys have seen that variable, but Q, volumetric flow rate. Okay, so that's conservation of mass. So that's going to tell us, relate, like how the velocities, how do those all relate to each other? So we can write now Fx equals, so it would be rho U1 squared A1 plus rho U2 squared A2, which would be equal to density Q squared over A1. Sorry, where I lost my sign convention. So I'm supposed to have a negative here, a negative before the A1, plus Q squared over A2. Okay, I could alternatively go in and like calculate what the velocities are and figure that out, but I don't actually have to, so I'll kind of save myself a couple extra calculation steps. But you can do it either way. It doesn't particularly matter. So that pretty much gets us to the entire right-hand side of the equation, right? So f of x equals rho q squared 1 over a2 minus 1 over a1. We know, or can really easily calculate, because we have diameters. But okay, we have to calculate areas, but we know all that. So now it comes to what's happening in Fx, and what does that actually mean, and what are the different forces that are involved. So this would tell us what's the net force in the x direction that is causing the acceleration that we're viewing, right? You're coming in, the fluid's coming in slowly, it's shooting out in a really fast jet. That's a force that has to cause that acceleration. This would tell us the force that is causing that acceleration, but it's not breaking it down into the different pieces. And we need it broken down into the different pieces because we care about how hard we have to push to keep that end cap up. Right? So we care about one specific thing. So we have to look at what forces matter. So Fx is all the forces, is the net force on the CV so it's the net force that's leading to this acceleration, but it's made up of multiple pieces. So we kind of briefly said this the other day, but just to reiterate, because this is a part where that is going to get tricky to handle and kind of confusing. So it's made up of a couple components. The first one is pressure. The second one is gravity. That's simply the weight of the fluid inside of our control volume. And the last one, which we'll call Rx, this is the reaction force. This is from some solid object. So typically when we're talking about like forces from fluids, pressure, forces from solid objects like this little end cap thing, that's a reaction force. So those two things are both surface forces. They're forces acting on the surface of our CV. Obviously, gravity is a body force acting on the entire volume. For this specific problem, we have a couple things. So we have pressure acting on side 1 and pressure acting on side 2. Right? Pressure is pushing in on all sides. We have gravity, which is the weight of the fluid. It's in the I don't know, I guess I don't know which orientation this is relative to the ground, but we're going to have really big pressures. So the weight of the fluid is going to be, right, it's a relatively big, like 10 centimeter pipe, but the weight of the fluid is not going to be big compared to the other forces. So even if it's oriented in line with gravity, it's not going to be very important. So gravity, close enough to 0 that we don't have to care about it. Maybe it's exactly 0 because gravity is in like the y direction. I don't really know. Maybe gravity's acting down and it's exactly 0 in the x direction. And then the last force is the reaction force. Are there any solid objects pushing on our control volume? Obviously, there's not at side 1. There are solid objects, right? There's the pipe walls, but those aren't in the x direction. So the only solid object pushing in the x direction is that end cap. So if we look at what those forces are, we're left with F Sx plus 0 plus Rx. And that equals, well, we'll just write this rather than putting that other stuff in there yet. So now let's pull out this one specifically. So this is force that's the force our end cap applies to the control volume. This other one, this is pressure. So we've already done stuff with how pressure exerts forces. We've done a lot on, right, how does pressure exert forces on objects? We did a lot with that. So this would be, right, the minus P dA. We could say, okay, it's the pressure at the centroid times the area that would be the magnitude of that resultant force. that we do it's exactly the same. It just so happens a lot of times in these types of problems, pressure doesn't change with height enough to really matter, because your whole thing is 10 centimeters and your pressure is 130 megapascal. So you're going from 130 megapascal at the top to 138 megapascal at the bottom. So everywhere is 138. You just have like this teeny tiny change. So we usually can kind of forget that we're doing the exact same thing, but we're doing the exact same thing that we just did in like finding resultant force on an object. We're finding the resultant force on, say, surface 1 and surface 2. So on surface 1, again, we use this kind of notation to keep our, that should be a vector, to keep our sign conventions working right, but pressure is going to be pushing in it's always going to be pushing in. So this is minus P1, and then, well, minus and then negative P1 A1, because A1 is in the negative X direction, plus minus P2 A2. Our P2 is atmospheric pressure. So this is why gauge pressure is nice, because we don't even have to worry about that term. So this equals just P1 A1. Okay, so now let's plug all of this in and then we're almost done. So P1 A1 plus Rx is equal to rho Q squared 1 over A2 minus 1 over A1. And then if we plug in numbers, this would be Rx equals, to be minus 138 times 10 to the 6 pascals times A1, which is pi over 4, 1 times, what is it, 100 millimeters, so 0.1 meters. That would be A1 plus 1,000 kilogram meter cubed, 0.57 meters cubed per second squared. 1 over A2, which is pi over 4, 0.038 meters squared. And then I'm running out of space. Move that over a little bit. 1 over pi over 4. No. 0.1 squared. Okay, lots of parentheses. Okay, if you plug all that in, you'll get Rx equals negative 839 kilonewtons. So this is just a couple ways to think about this, right? What we're calculating, we're looking at the world from the perspective of the fluid. So from the perspective of the fluid, in order for this process to be happening, there has to be this reaction force pushing to the left on me, the fluid. in order for me to be shooting out of this thing the speed that I am and like doing for this flow to be happening. So right there's for everything there's an equal and opposite every reaction there's an equal and opposite reaction. So there's a force on me, the fluid, of 839 kilonewtons to the left, or I am exerting a force on the end cap of 839 kilonewtons to the right. So I'm pushing to the right, but the thing is pushing on me to the left. So we're always, when we're doing this, how we're viewing it from the perspective of the fluid. And you're really looking at, right, what is the, right, that's going to be related to here, like the momentum that's coming into the system and the momentum that's leaving the system and pressure are going to be kind of the things that are happening. So there's a force from the momentum of the fluid coming in. There's a force or a momentum that's leaving the system, which is like the fluid leaving at a certain velocity. There's the mass flow rate times the velocity. And there's the pressure term that hangs around. So when you get, I don't know, maybe you can see it, when you get into some of these more complicated problems, it can be hard to figure out what signs you should use and what things matter. I think it's something, there are some good examples in our book as well in this chapter. Just one last thing to end on before we leave for the weekend. I want to talk just briefly about, and we only have like 4 minutes, but if you run into something like this, which you will on, I think, problem 4 of the homework, be somewhat similar to this. If you have something that goes like this and changes direction, so the examples that we've done so far in class have all been a single direction. If you have something like this where, right, this is, say, surface 1 here, this is surface 2 up there, and you're flowing around this corner. How we're going to handle this is the exact same way that we handle things in one dimension. You just have to do kind of 2 separate problems. So we'll split this into X and Y problems. So they might have different forces in X and Y, because you might have, like in Y, maybe you have gravity, but gravity doesn't show up in X. So you may have things like that. But they're basically going to be the same problems. You just have, so this would be some over our control surfaces. The X direction is the X component of the velocity times rho v dot A. The Y problem is going to be the Y component of the velocity, rho v dot A. So this would be now the X component. We have 2 surfaces, so it will be U1 rho V1 dot A1 plus U2 rho V2 dot A2. This is going to be equal to little v1, which, right, little v is the Y component of the velocity. Rho. Capital V vector is the velocity vector. So 2 slightly different things. I don't think it'll be till Monday before we really start to parse out how that is different. V1, V2, we should have 1s on them, V2 rho dot A2. So you're going to be solving these 2 problems independently. You can look just at X first, then just at Y. One of the kind of things that might feel a little weird is there are things that are happening in one direction that are not happening in the other direction. So for example, what is the X component of the velocity U1 at side 1? It's 0. So this equals exactly 0. So that whole term dies because there isn't an x component there. It's going exactly in the y. Similarly, what's the y component at part 2? It's exactly 0. So that term will die. You may have similar things happening with pressure. Right? Pressure always pushes perpendicular. It always pushes in on a surface. So you have pressure acting on side 1, but that's acting in the y direction. It's not acting in the x direction. So it doesn't show up there. The pressure pushing on side 2 is pushing in the x direction, not the y direction. So you have to be careful, like which direction are things happening in? And that part can get a little tricky, but you're dealing with these as two completely independent problems. You're looking at everything just in the x, and then you flip yourself and look at everything just in the y. But other than that, I mean, it solves the same. It just solves it's kind of like 2 for the price of 1. Then you'll end up with an x component of the force and a y component of the force. And you could do that to calculate like total forces and angles and some fun stuff like that, which you'll get a chance to do. All right, so that wraps us up for this Friday of week 5, which is kind of exciting. So it's officially a third of the way done. Oh, you're in class saying, I do not want it. Keep it. It might be useful for you as you're doing homework. So I'll have it due. If you want to turn it in on Moodle to save yourself the headache, that's fine. Otherwise, you can turn it in on time. Wow.